Huffman coding is a classic compression algorithm that assigns shorter codes to frequent characters. Today we'll build it entirely from scratch in a single Java class. You'll see how a priority queue builds the tree, how codes are generated, and how we compress and decompress text losslessly. We start with a private inner class node that represents a tree node. It stores a character, its frequency, and references to left and right children. Internal nodes store a null character 0 and a combined frequency. isLeaf checks if the node has no children. The compareTo method compares frequencies so the priority queue can order nodes correctly. Build frequency map iterates over every character in the input text and counts how many times each character appears. It uses hashmap.merge to increment the count efficiently. This map is the foundation for building the Huffman tree. Characters with higher frequency will later get shorter codes. A priority queue holds all leaf nodes. We pull the two nodes with the smallest frequencies, combine them into a new parent node with their total frequency, and add it back. This process continues until only one node remains, the root of the Huffman tree. This greedy algorithm guarantees optimal prefix codes. Starting from the root, we recursively traverse the tree. Moving left appends 0 to the code, moving right appends 1. When we reach a leaf node, we store the accumulated binary string in code map. The special case code.length 0. Code 0 handles input with a single unique character. Encode ties everything together. It builds the frequency map, constructs the tree, generates the codes, and then replaces each character in the original text with its binary code. The result is a long string of zeros and ones representing the compressed data. Decoding starts at the root and follows the bits, 0 goes left, 1 goes right. When a leaf is reached, we output its character and reset to the root. This process perfectly reconstructs the original text because Huffman codes are prefix-free, no code is a prefix of another. The main method uses the classic example string. This is an example for Huffman encoding. It prints the frequency table and encodes the text, shows compression statistics, original ASCII size versus encoded bit length, and then decodes it. Finally, it confirms the round trip is lossless. The program compiles and runs cleanly. The encoded text uses 135 bits instead of 312, achieving over 56% compression. Decoding perfectly reconstructs the original string, proving the algorithm works correctly. You've implemented Huffman coding from scratch. This algorithm is used in zip, JPEG, and MP3 files. Understanding it teaches you greedy tree construction, prefix codes, and lossless compression fundamentals. With this knowledge you can now compress and decompress data in your own Java apps.